in our section 5, we're going to take a look at false positives and false negatives. And this is something that typically appears in the medical field. Anytime that you're running a test of some sort, you can get a false positive or false negative. So let's talk about what that means. So if the test says yes, so if it comes back as yes, does it actually mean yes? So it could be wrong when it says yes, or it could be wrong when it says no. And that's how we get a false positive and a false negative. So the kind of best way to understand false positive and false negative is looking at a table. So the test comes back and it says that you do have whatever it says, and you really do have it. So that's a good thing. That means the test was right. Now on the next say, the test could say that you don't have it, but you really do. And this is what's called a false negative. It's when the test comes back as no, but it really shouldn't have. And then for a false positive, the test comes back and says, yes, you do have this, but you really don't. And that's a false positive. And the last one is the test comes back saying you don't and you really don't. And this would also be correct. So the test is also right. So let's talk about two examples of something that could come back as a false positive or a false negative. One of them in more recent years you can probably think of is COVID-19. Right? If you get a COVID test and it came back as positive, but you don't really have COVID, that would be a false positive. Or you could get a test and it comes back negative, but you really do have COVID, which is a false positive. Another kind of important example, it would be cancer screening. So you could come back, the doctor says you test positive for a certain type of cancer, but you don't really have it, and vice versa. So let's go ahead and take a look at an example. So Hunter says she is itchy, and there is a test for allergy to cats, but this test is not always right. For people that really do have the allergy, the test says yes 80% of the time. And for people that do not have the allergy, the test says yes 10% of the time. And this is what we call a false positive. So if you look at this in terms of a table, if the test says yes and Hunter really does have the allergy, that probability is 80%, which means that the false negative rate is 20%. So you have the allergy, but the test says no 20% of the time. On the reverse side of things, if you don't have the allergy, the test says yes 10% of the time. This is our false positive rate, which means the test says no and you don't really have the allergy 90% of the time. Now this doesn't work the same way as a table that we were looking at before. It's not like in this case my row and my column are going to add up. In this case my row adds to the 100%, not my column. Because if I look at my columns here, one of my columns is 90% and the other column is 110%. So we're looking at the row, whether you have the allergy or you don't have it. And based off of this information, what we're trying to figure out is if 1% of the population actually are allergic to cats and Hunter's test says yes, what are the chances that Hunter really has the allergy? So we're trying to figure out how accurate is this test. And there are two different ways you can figure this out. One method is to literally use numbers, and the other method, which is the method I kind of prefer, is to create it as a diagram. So let's look at our first example, which is using numbers. So it's called Imagine 1,000. So what you do is you take all your percentages and you convert them to numbers. So imagine a large group, say 1,000 people, and what we do is we play with the numbers. So in 1,000, your total true positive out of 1,000 is to multiply 1,000 by your number of positives. So if the test comes back as positive 1% of the time, that would mean 10 people in a group of 1,000 are allergic to cats because our true positives were 1%. So this was 1%. So then for our total true negatives, so 99% of people aren't allergic to cats, would be 990. And then that's how we get our total of 1,000. Now let's go back to our test results. So tested positives that are actually positives. So this is our 80%. The test comes back, 80% of the 10 people that are allergic to cats actually are. So in this case, 80% of 10 is 8. So that means our false negatives is our 20%, which in this case is 2. So those are the people that test positive for having an allergy to cats but aren't actually allergic. Okay. Now let's look at our true negative. So these are the people that aren't allergic to cats but test positive or test negative. So our test positive from this, that's our false positive. So we know 10% of people test positive but aren't actually allergic to cats. So what we're doing is we're finding 10% of our 990, which is 99. So now we're going to look at our negatives. So those are the people who test negative and are actually negative, which we know the test then comes back 90%. So 90% of 99, which 990, which is 891. So now we're going to find our totals. So the total number of people who test positive is 107. And then the total number of people who test negative is 893. So now we want to find the actual probability. So the probability that a positive test actually identifies a true positive result. What we do is we take our number of tested positives that are actually positives, which in this case is 8, and we divide it by the total number of people who tested positive, 107. And that gives us 0.075, which is 7.5%. And then to get the probability that a negative test result actually identifies a true negative result is we take our number of negatives, true negatives, 891, and we divide by the total number of people who tested negative, 893. And we're going to get 0.998, which is 99.8%. So the test is actually really good at identifying people who aren't allergic to cats. And then on the reverse side of things, the probability that a positive test actually identifies a true positive result, only 7.5%. So the test isn't that great at identifying people who are actually allergic to cats. So that was our first method. Our second method is with something called a tree diagram. And what it does is it takes the Imagine 1000 scenario that we just did and makes a visual representation of it, which I find to be really helpful, much more so than the example we just did. So how it works is you start with your population. Right. Then you have your first set of branches, and it really depends on the situation. You have to have a minimum of 2 branches to start here, but you can have more than that. In this case, we actually break down first for 2 branches, and that is whether or not you have the allergy, so whether you're allergic to cats, or you don't have the allergy. And this is where our 1% and the 99% come into play, which in a tree diagram, we always leave as percentages, so probabilities, 0.01 and 0.99. Now, from our have allergy and don't have allergy, we then have 2 more branches. And that can either be that you get a positive test result or a negative test result. And these are the same branches for the top and the bottom. And we know if you have the allergy and you have a positive test result, that happens 80% of the time, so 0.80, which means negative test result 20% of the time. And then for the don't have allergy, you get a positive test result 10% of the time, which means you get a negative result 90% of the time. Now here's the thing, in a tree diagram, each set of branches, those probabilities have to add to 100%. So my first set of branches have allergy, don't have allergy, 0.01 and 0.99 adds to 100%. Then for have allergy, positive and negative test, 0.80 and 0.20 add to 100. And then don't have allergy, positive and negative, 0.10 and 0.90 add to 100. Now to find the percentage that a positive test I define as you actually have the allergy. So you are going to do a fraction. So the way that this works is my numerator is positive, have the allergy, and tested positive. So that's going to be multiplying 0.01 times 0.80 because you have the allergy and you tested positive. My denominator has to be the probability that you test positive. So there's two incidents that you test positive. That's you have the allergy and you tested positive, so 0.01 times 0.80. Or it could be that you don't have the allergy and tested positive, so 0.99 times 0.10. So my denominator has to account for the false positives as well. So in our numerator, 0.01 times 0.80 is 0.008. And then in the denominator, we get 0.008 plus 0.099, which is going to give us 0.008 over 0.107. And if I convert these back to whole numbers, it's 8 over 107, which is what we got when we did the 1,000. So we get 0.075, which is 7.5%. So that means that both methods work and give you the exact same answer. I personally like tree diagrams better. It's a nice visualization for me. I'm much more of a visual person. I don't like the imagine 1,000 because my brain just doesn't work that way. So let's go ahead and take what we just did and do an example. So at the Fairtown High Court, people on trial are judged as follows. For people who are really guilty, the judgment says yes 97% of the time. And for people who are in fact innocent, the judgment says yes 4% of the time. So that's our false positive. People who are innocent found guilty 4% of the time. So if 72.5% of people on trial really are guilty and the judgment for a randomly selected person says guilty, what are the chances that person really is guilty? So let's start by creating our tree diagram for this situation. So our population here is people on trial. And there are two outcomes. You can either be guilty or innocent. And we know that people are found guilty 72.5% of the time, so that's 0.725, which means people are found innocent 27.5% of the time, which is 0.275. Okay. From guilty and innocent, we have two more branches. You really are guilty, or you're not guilty. It's the same way down here. So guilty and not guilty. And we know from above that people who are really guilty, you are found guilty 97% of the time. So that's 0.97, which means they're found not guilty 3% of the time. And then for our false positives, so people who are innocent but found guilty 4% of the time, so 0.04, which means innocent people are found not guilty 0.96. Now we're going to find the actual probability, chances someone really is guilty. So for our numerator, we want guilty and guilty, so you actually are guilty, 0.725, or you're found guilty and you really are, so 0.725 times 0.97. And then for our denominator, we have the 0.725 times the 0.97 again, but then we also have to do our false positives, so 0.275 times 0.04. So for our numerator, we're going to get 0.703, and in the denominator, we'll get 0.703 plus 0.011, which becomes 0.703 over 0.714, which is 0.985, which is about 98.5%. So that's really good. So if someone comes back guilty, there's a really good chance that the person really is guilty. So let's talk about same situation. 72.5% of people on trial are really guilty. Judgment comes back innocent. What are the chances that person really is innocent? So I'm not going to redo the tree diagram. It's the exact same tree diagram. But now we're going to go off of innocent. So our numerator is innocent and you're found not guilty, which is 0.275 times 0.96. And then for the denominator, we'll have the 0.275 times 0.96 plus your guilty and your found innocent, which is 0.725 times 0.03. So that becomes 0.264 over 0.264 plus 0.022, which is 0.264 over 0.286, which is 0.923, which is about 92.3%. So still pretty high. Comes back innocent, you really are innocent, 92.3%. So slightly smaller percentage than if you are guilty and it comes back guilty, but still in the 90s. So I'd still say that this court is a pretty good court. So let me know if you have any questions about what a false positive or false negative is, or if you have any questions about tree diagrams.